Welcome to Matcom. In this particular video, we will be discussing about a question from NCERT Chemistry Class Plus 2 textbook, Organic Chemistry part, in the chapter Alcohol, Phenol and Ether. The question is, ortho and para nitrophenols are more acidic than phenol. Draw the resonance structure of the corresponding phenoxide ion. So they're telling like why ortho and para nitrophenols are more acidic than phenol. We need to establish our answer by using the resonating structures of the corresponding phenoxide ion. When you consider their structures, whenever you are having a benzene ring, to a benzene ring, if an OH group is attached, that is called a phenol, and to a phenolic ring, if nitro group is attached to the para ortho position, that is called ortho nitrophenol. If a nitro group is attached to the para position, that is called para nitrophenol. So this is phenol. This is ortho nitrophenol. Next is para nitrophenol. When you consider the acidic property, we know that the acidity is the capacity to or the ability to donate H plus ion. Donate H plus ion or donate proton. If any species is donating H plus ion, it will be becoming an anion. If that corresponding ion which is formed is more stable than the parent molecule, we can very easily say that that molecule can easily donate H plus ion or that will be more acidic. For example, if you are considering a compound called Ha, by donating the proton, it will be becoming H plus and A minus. If A minus is more stable than Ha, if A minus is more stable than Ha, we can say that Ha is highly acidic. Why we can say that Ha is highly acidic? Since A minus is more stable than Ha will be having the tendency to become A minus by donating H plus ion. If any species is donating H plus ion readily, that species can be called as highly acidic. In the same way, when you are considering phenol, orthonitrophenol or paranitrophenol, if phenol is donating an H plus ion, it will be becoming a phenoxide ion. By donating H plus ion, phenol will become phenoxide ion. That is called O-. This is called a phenoxide. We know that phenoxide ion is more stable than phenol. Since phenoxide ion is more stable than phenol, phenol is acidic. We will see in another video why phenoxide ion is more stable than phenol. If I explain that particular thing also here, it would become a very lengthy proposition. Then when you're considering in the case of an orthonitrophenol, by donating an H plus ion, it will become like orthonitrophenol ion. Orthonitrophenol. By donating an H plus ion from a paranitrophenol, you will be getting paranitrophenol. When we are comparing the stability of phenoxide ion, orthonitrophenol ion, as well as paranitrophenol ion, this paranitrophenol ion and orthonitrophenol ion are more stable than phenoxide ion. Why? Because now, for example, by a layman understanding, you can understand when you're considering an NO2 group, NO2 is an electron withdrawing group. NO2 is an electron withdrawing group. Due to the presence of an electron withdrawing group, in the corresponding phenoxide ion, the oxygen will be bearing a negative charge. This particular NO2 group will pulls the electron cloud. NO2 group will pulls the electron cloud which is present in the corresponding phenoxide ion. That means that will reduces the charge density in the molecule. whenever the charge reduces, stability will automatically increase. If something is existing in a charge state means its stability will decrease. It will become highly reactive. That is why due to the presence of an NO2 group, this particular NO2 molecule reduces the electron charge density from the benzene ring as well as from the oxygen. That means this particular phenoxide ion or the negative charge which is present on the oxygen gets stabilized by the presence of an electron withdrawing group. When you're considering the phenoxide molecule, in the phenoxide molecule, there is no corresponding structure like that. That is why the orthonitrophenoxide ion and para-nitrophenoxide ion is more stable than phenoxide ion. Then assume that other than having a electron withdrawing group, if it was supposed to with an electron releasing group, it will enhances the electron density in the ring, or it will enhances the negative charge density in the oxygen. Automatically, the stability of the corresponding phenoxide ion decreases, acidity will decrease. Okay, clear. This particular proposition can be explained by using the resonance structure. So first we will see the resonance structure of orthonitrophenoxide. Orthonitrophenoxide. When you're considering an NO2 molecule can be drawn in two ways. For example, N double bond O like this, or you can draw like N double bond O, O minus, En plus. Both are correct, but this structure would be more accurate to explain the resonating structures. Why the positive charge is coming? We know that the valency of nitrogen is 3. Whenever one more bond is formed with respect to the oxygen, or any one more bond is formed, that is utilizing the electron present in the nitrogen. That is why nitrogen will be becoming positive over there. So when you're trying to draw the resonating structure, when you're considering the orthonitrophenol, this is basically called what is called a orthonitrophenol. Then when it is undergoing resonating structure, we know that this negative charge can be shifted between these two carbon. When it is shifted between not carbon, between the oxygen and carbon, in order to maintain the valency, this bond will shift to this carbon. When this bond is shifted to this particular carbon, not to the bond, it should be shifted to the carbon. Why? Because of the reason now. This will be shifted to get shifted between the carbon and nitrogen. When it is getting shifted, this bond will get shifted to the corresponding oxygen. So what will you get? We will be having the ring. In the ring, we will be having C double bond O, double bond N, O minus, O minus. Whenever you are drawing the structures, be very careful how the bond is shifting. Once you given the skeleton, give the bonds and check whether everything is right. The next step, what can happen? In the next step, any one of this particular double bond can come back. This particular bond will shifted between these two carbon. This bond will shifted to this corresponding carbon. So what will you get? You will be getting a structure like, we have a ring. There is a C double bond without any change. Between this one bond change, there is an N double bond O. NO minus is there. A bond is formed between these two carbons, and there is a negative charge will be created. The next step, this bond will get shifted between these two carbon. This bond will get shifted to this carbon. So what will you get? You will get here there is a negative charge because that bond is shifted. So there is a bond is formed between these two carbon. Here, then we have a N double bond O. Oh my. The next step, if you want to draw one more, you can draw it like this is shifted to here. This is getting back here. Okay. So I missed. There will be negative positive charges there. Okay, please be very careful. The positive charge is well maintained. Why? Because in all these cases there is 4 valencies associated with the nitrogen. Nitrogen valence is 3, so one more bond is formed means we need to give a positive charge. So the next structure will be CO minus, double bond, double bond, double bond, N double bond, O minus, plus. So when you're considering the resonating structure of the orthonitrophenoxide ion, we can see that the negative charge by comparing the first and the second resonating structure, we can see that the negative charge which is generated or the negative charge is withdrawn by the electron withdrawing nitro group. Correct? Electron withdrawing nitro group. Which is this effect? How the negative charge is withdrawn? The negative charge is withdrawn by the resonance. That is why we can say that the minus R effect of NO2 group, because it is not pulling the effect, rather than that it is pulling that particular electron cloud by using the process of resonance. Okay, minus R effect. Where you can see the minus R effect, you can see the minus R effect here. Clear? Then, so first we have seen the resonating structure of those. Then, if you consider resonance structure of or the resonating structure of para-nitrophenoxide ion, if you consider phenol, so para-nitrophenoxide ion, so we are having O minus, we are here with N, double bond O minus, the nitrogen will be having a positive charge. First step, bond will be shifted between these two carbon. This bond can shift to this particular carbon. So what will you get? You will get C double bond O. A negative charge will be generated. The remaining bonds will be like as such. What will be happening for the next step? Next step, this electron pair can form a bond between these two carbon. This bond will shifted between these two nitrogen. This bond will shifted to this particular between nitrogen to this particular oxygen. So what will you get? So you will be having a cyclic ring. To this ring, there is a double bond O. A bond is formed between these two carbons. So by shifting of this particular bond, a bond will be formed between the carbon and nitrogen. Due to this lone pair, double bond is shifted to the oxygen. This oxygen will get a negative charge. This oxygen will get a negative charge. Nitrogen will be having the positive charge. The next step, the bond will get shifted. This bond will get shifted. As a result of it, the bond will shift and forming a negative charge in this particular carbon. So double bond O, negative, a bond is formed, N O minus, double bond O plus. Last step. Right? No other issues are there. So when you're considering this particular structure also, we can understand that the negative charge which is generated in the ring as a pass of resonance is withdrawn by the NO2 group by resonance. So where here there is a phenomenon is acting, this is called a minus R effect of NO2 group. Due to minus R effect of NO2 group, the negative charge which is delocalized in the ring is getting withdrawn or by reduced by the NO2 group by negative resonance. Okay, so the charge density will get decreases, stability will increase. When you're comparing or when you're seeing the resonating structure of the phenoxide ion, seeing the resonating structure of the phenoxide ion, such a stabilization is not possible. So we can see that will also I will discuss here. So when you are considering resonating structures of resonating structures of phenoxide ion, sorry, the first step, bond will be formed between these two carbon. Already existing bond, negative charge will be getting accumulated. Next step, negative charge shifted, bond formed, the other bond will be shifted to the corresponding carbon. Last step, see when you're considering the resonating structure of phenoxide ion, the negative charge is getting accumulated at the ortho and para position, but there is no group to withdraw that particular negative charge density. But such a stabilization is possible for orthonitrophenol as well as paranitrophenol. That is why orthonitrophenol ion as well as paranitrophenol ion is more stable than phenoxide ion. So since such phenoxide ions are more stable, that will be more acidic in nature. Here we can explain one more point. It can be written as minus I effect of NO2 group. That is not predominant. That is called negative inductive effect. That means from the ring itself, the NO2 having a electron pulling effect. That means it has a tendency to pull back the electron density from the ring. Such can also stabilize as the ring system. But the predominant factor is minus R effect of NO2 group. So we have seen why orthonitrophenol and paranitrophenol are more acidic than phenol by using the resonating structure of corresponding phenoxide. If you're having any doubt, do let me know. Or if you want to explain any other concepts in organic chemistry or in physical chemistry or in organic chemistry, even in analytical chemistry, please comment it. I will answer to that as much as possible. If there is any change or any modification is expected from your side, do let me know. Otherwise, as a token of gratitude, please like the video, please comment upon it, as well as please subscribe to the channel. Thank you. Thanks for watching. Keep learning chemistry. Keep enjoying chemistry. Thank you. Thank you so much.